Maria is ready.
Okay, excellent. So, well, welcome back. So the next speaker is going to be María Inés de Frutos-Fernández, and she's going to be talking about formalizing local fields in Lean. Is Maria here?
We can't hear you, Maria. It looked like you were talking.
Can you hear now me? We see your slides.
Yes, now we're good.
Okay, good. Okay, so yeah, go ahead.
So should I start now then?
Yes. Sure, yeah.
Okay, perfect. So yeah, thank you very much for the invitation to give this talk. Everything that I'm going to discuss today is joint work with Filippo Nucchio. And in this project, we were trying to formalize in Lean the definition of local fields and also some of the basic properties of the theory of local fields. So by local field, today I mean a non-Archimedean local field. So that is a field complete with respect to a discrete valuation and such that the residue field of this field is finite. So in particular, whenever I say local field, I'm never going to be referring today to the real numbers or the complex numbers. I am only going to be referring to the non-Archimedean case. Okay, so I want to mention that we plan to integrate all of the results that we formalized in this project into Mathlib. And of course, this means that we have to formalize everything in the correct degree of generality. Right, so I mentioned this because most of the results that I will discuss today don't need the hypothesis that the residue field is finite. And also there's a few of them that do not need the hypothesis that the field is complete with respect to the evaluation. They only need that the evaluation is discrete. So we have tried to formalize everything in the correct degree of generality. And because of that, I'm going to split the talk in three parts.
I just want to, sorry, Maria, it seems that some people are having trouble seeing the slides. And actually, we're only seeing the title slide right now. I don't know if that's normal.
That's weird. Okay, let me...
That's not normal. Okay.
Let me stop sharing and start again. Maybe... is this better?
As a precautionary measure, based on yesterday, what happened with the other speaker, perhaps you'd like to post your slide PDF on Zulip immediately, because then I can be ready to share it just in case something is going wrong.
I mean, it looks like we don't see the presentation mode of the PDF.
That could what be. Happens? Yeah, I think some people were seeing only the were only seeing black, and and other people only saw the title slide.
So yeah, I can post it on Solib.
I think I might have experienced this kind of thing before, and I think it may help if you're not sharing something that's full screen, but I'm not sure.
Okay.
Yeah, that might be worth trying.
Sorry. The wrong stream, but probably we can fix that later. Okay, so let me try to share again. Okay, do you see something now?
Yes.
Okay.
So now we see the outline slide.
Okay, and if I do it presentation mode, do you still see it or not?
Yes.
Yeah. I see it.
Okay, great. Then hopefully.
Yeah, I see it now.
All right.
Sorry about that.
Let's try this.
Okay. So yeah, I was saying that I'm going to split the talk in three parts. So in the first part, I'm going to talk about the theory of fields with a discrete valuation and how these are related with discrete valuation rings. And then once we have developed this more general theory, we will focus on the case of most interest to us, which is the case of local fields. And finally, I will say a couple of words about what we plan to do in the future. So when I say valuation today, I mean a multiplicative valuation. So that is a map V from a ring R to a group with 0 that satisfies the following property. So I want the valuation of 0 to be equal to 0, the valuation of 1 to be equal to 1. I want this function to be multiplicative. And I also want it to satisfy the strong triangle inequality. So that means I want the valuation of the sum of two elements to be less than or equal to the maximum of the valuations of the elements. And we also will need to consider the unit pole of the valuation. So this unit pole is defined as the subset of elements in the ring that have valuation less than or equal to 1. And it can be proven that this unit pole is actually a subring of the ring R. to give you a concrete example to keep in mind, we can start with the ring set of integer numbers and any prime number p, and then we can define a function that I'm going to call the additive periodic valuation. And this function is going to assign to a number r the maximum power of p that divides r. Of course, 0 is divisible by any power of p, so in that case, I'm going to set the additive valuation of 0 to be equal to infinity. Once we have defined this on the integers, we can extend it to the rational numbers by saying that the additive valuation of a fraction is the additive valuation of the numerator minus the additive valuation of the denominator. So in particular, for some examples, if we consider the number 18 and the prime p equal to 3, then 3 goes twice into 18. So that means that the 3-adic valuation of 18 is equal to 2. Or for example, the 2-adic valuation of 5 divided by 16 will be -4 because 2 appears 4 times in the denominator. Now, this is not a function that has the properties in the previous slide, but we can construct such a function by sending a rational number x to the power of p given by the negative of the additive valuation. So this is a function that takes values in integer powers of p union 0, and it can be checked that it satisfies all of the properties that we wanted for a valuation. A technical point here about the formalization is that it is kind of annoying to working with this p to the integers union 0. It's not very clear how we will want to define that. So instead, we work with some abstraction of that. So we have multiplicative set, which will be a generalization in some sense of this p to the set, where we don't need to fix a base number p. And then to that, we add 0. So that type is going to be denoted in the slides by set m0. Okay. Now, we will focus today on discrete valuations, and a valuation is going to be discrete if the codomain of the valuation is this type set m0, and the valuation is surjective. And then some examples of discrete valuations will be the p-adic valuation on the field Q of rational numbers, or the x-adic valuation, which is constructed analogously on the field fqx of rational functions in one variable over fq. Discrete valuations are special in some sense because there are one of the properties that make them special is that it can be shown that a discrete valuation taking values in set m0 is discrete if and only if there exists a uniformizer for b. So what is a uniformizer for b? So that will be an element pi in the field k, which has additive valuation equal to 1. In the formalization, we don't work with the additive version of the valuation, we work with the multiplicative version of the valuation. So to say that something is a uniformizer, we need to say that the valuation of this element pi is equal to the multiplicative version of the element -1. That will be equivalent to saying that it has additive valuation equal to 1. Okay, so we have formalized this equivalence that the valuation is discrete if and only if there exists a uniformizer. And then we use the existence of uniformizers to get some nice results about the unit ball. The first thing that we prove is that if we take any element r in the unit ball k naught of this valuation, we can always express this element r as some natural power of a uniformizer times 1 unit element. And then using this result, which we have called Poe uniformizer in our formalization, we can conclude several things. So the first thing that we can conclude is that the maximal ideal of the unit ball is actually generated by any uniformizer for the valuation. And then more generally, we are able to conclude that any ideal of the unit ball is generated by one element. So that is, it's going to be a principal ideal. And using this, we are able to relate the notion of having a field with a discrete valuation, and we are able to relate that with discrete valuation rings.
Excuse me, Maria.
Sorry?
Maria, you've been going very fast, and I lost the. What is the definition of K0 here?
K naught is the unit ball, so they are the elements that have valuation less than or equal to 1.
Okay, thanks. Can you briefly show the previous slide again? Just because it was really, really fast.
Yeah, sure. Yeah, so what we do here is we show that any element r in the unit ball is a natural power of a uniformizer times a unit in the unit ball. So a unit, I mean an element that has a multiplicative inverse in this case. And then using this, we are able to conclude that the maximal ideal of K0 is generated by any uniformizer.
So can you restate this in the example of Q or so for rational numbers with a p-adic norm, what does this say?
Yeah, so for the p-adic numbers, this will tell you that, well, in that case, the unit ball will be the p-adic integers, set p, right? And this theorem tells you that the maximal ideal of set p is generated by any uniformizer. So for example, you can take p, right? So it tells you that the maximal ideal of set p is generated by p. Does that make sense?
Sure.
Okay. Okay. Yeah, so yeah, we want to relate discrete valuations and discrete valuation rings. So a discrete valuation ring is going to be an integral domain which is local, in which every ideal is principal, and which is not a field. So this is one of a few equivalent definitions that are already formalized in MATLib prior to our work. And what we did here is we proved that if K is a field with a discrete valuation V, then the unit ball K0 is always a discrete valuation ring. And basically this follows from the result Pau uniformizer in the previous slide. And then conversely, we want to prove that if we start with a discrete valuation ring A, we can always put a discrete valuation on the fraction field of A. And the way that we do this is, well, we know that A has a unique maximal ideal A, and to this maximal ideal, we can associate an adic valuation in the same way that to the number, the prime number P, we can associate a p-adic valuation. And then that gives us a way of putting a valuation on the fraction field of A. And this was already done in some sense, but what we did now is we proved that this valuation is always going to be discrete. Okay. Now, for the next couple of results, I need to assume something else. I need to assume that the field K is complete with respect to a discrete valuation. And then if I assume that, and I also assume that I have a finite extension L over K of fields, then I can prove that I can always put a unique discrete valuation W on the top field L, which induces the valuation V on the bottom field K. And also I can prove that L is complete with respect to this new valuation W. There are several ways to prove this result. And the approach that we follow is the one that I sketched here. So first, we already had, by some previous work that I did to formalize the definition of the p-adic complex numbers, we already had the fact that under the hypothesis of this proposition, there is always a unique valuation W prime on L that extends the valuation of V. So by that, I mean that if I take any element X in K, I can regard that element also as an element of the bigger field L. And then the valuation V of X will be equal to the valuation W prime applied to X. Now, the problem with doing this, in some sense, is that this valuation has a bigger codomain than set M0. In order to do this, in some sense, informally, what I'm doing is I need to be able to take rational powers of elements of set M0 in the codomain. Of course, we have to be careful about how we do this in Lean, in the formalization, and I won't get into the details of how we do that in this talk, but we were able to do it. And then in order to get a discrete valuation, what we have to do is we have to renormalize this W prime valuation in some sense. So essentially what we have to do is we have to find the correct integer so that if we raise this W prime to that integer, we get a normalized valuation. So a valuation W on L, which is surjective onto set M0. Okay. And then in the same setting as in this proposition, we were also able to prove that the integral closure of the unit ball of K inside the bigger field L is actually equal to the unit ball of the bigger field L. So in particular, this tells us that this integral closure is always going to be a discrete valuation ring. Okay, and then the next general results that I want to talk about are results about localizations. So something that was already done in Mathlib is that if we start with a dedicated domain R, and I'm always going to assume that this R is not a field, we denote by K the fraction field of R and by P some maximal ideal of R, then the completion KP has a discrete valuation that extends the valuation P associated to this prime P. By construction, the completion is, of course, complete with respect to this valuation. So by the previous theorem, we have that the unit ball of KP is going to be a discrete valuation ring. Now, if you're familiar with these kind of completions, there's actually two ways to think about the valuation on KP. So one is the definition that I just gave you. So KP has a valuation that extends the valuation on K, just because KP is constructed as a completion of K. But then there is another way to get a valuation on the field KP. And that is because we have shown before that KP not is a discrete valuation ring. Therefore, by some of our previous results, we can give KP the adic valuation corresponding to the maximal ideal of KP naught. And in principle, this could be a different valuation because they are the definitions are different, right? Like they are constructed into different ways. But in informal mathematics, they are usually identified. And in fact, we formalize the proof that these two definitions actually agree. So they both give you the same valuation in KP. So this is this last lemma that I'm showing you here on the slide. Okay. So these are all the general results that we formalize about fields with discrete valuations. And using these results, we are now able to move on to the case of local fields. So a local field is defined as a field with a discrete valuation. So that is done in Lean by saying that the class local field extends valued get set them 0. And then we have to put three hypotheses on this valuation. So the first one is that this is a complete space. The second one is that the valuation is discrete. And finally, we want the hypothesis that the residue field is fine. So this is one, in some sense, this is the most abstract definition of local field that we are giving. But it can also be shown that local fields are always of two different kinds, and each of these kinds can be given a more complete definition. So we also did that in the formalization. So the first kind is a mixed characteristic local field, which is a finite field extension of QP for some prime P. So that's exactly how we define it. So we fix some prime number P, we fix some field K, we assume that K is not over QP, and then we just have to ask that the dimension is fine. Okay, so the first thing that we want to show is that this is a special case of the previous definition, and this is something that we formalize. A mixed characteristic local field is always a local field in the sense of the previous slide. Now, if you are familiar with the p-adic numbers in Mathlib, and you have paid attention to the code in the slide, you may have noticed that I am using some weird notation here for the p-adic numbers. I'm denoting them by q_p, but this is not the notation that we use for the p-adic numbers in Mathlib. And the reason for that is that in our formalization, we don't exactly use the same definition. So the p-adic numbers in Mathlib are defined by the Cauchy sequence completion of the rational numbers with respect to the p-adic norm. And then the p-adic integers will be defined as the subtype of elements that have norm less than or equal to 1. While in our formalization, we instead try to fit in without this, we try to fit in within this general setting of taking completions of dedicated domains with respect to some the valuation determined by some maximal idea. Right, so we define QP as the adic completion of Q with respect to the valuation determined by the prime idea generated by P. And then perhaps a bigger difference with the Mathlib implementation is that we define set P not as a subtype of QP, but instead we define it as the valuation subring of QP. And the reason we do that is because in Mathlib there are also some results formalized about valuation subrings in general, and we wanted to be able to access these results and not have to prove them again. But of course, we want to prove that our definition is equivalent to the one that is already in Matplotlib, which is in some sense, which is something that we formalize. We prove that these strings are isomorphic and they are also isomorphic as uniform spaces. Okay. Now, for any mixed characteristic local field K, we defined the ring of integers of K as the integral closure of set P in the field K. Now, by our previous result in the general setting of fields with a discrete valuation, we had shown that this integral closure is actually equal to the unit ball K naught. And in particular, this means that this integral closure is going to be a discrete valuation ring. Now, the second kind of local fields is what is called an equal characteristic local field, which is defined as a finite field extension of the field Fpx of Laurent series over Fp for some prime P. And every result that we were able to prove for the mixed characteristic case, we were also able to prove for the equal characteristic case. So the first one is proving that an equal characteristic local field is a local field in the sense of the first definition. And then again, I have to tell you a technical detail about the implementation, which is that what I denoted by Fp double parenthesis x in the previous slides is not actually defined as the Laurent series ring over Fp. It is defined as the adic completion with respect to the valuation corresponding to the ideal generated by x. And this is a completion of the field Fpx of rational functions over Fp. Okay, so in pen and paper mathematics, this identification is often not justified at all, but we did provide the isomorphism. So we did prove that this adic completion is actually isomorphic to the field of Laurent series over K. We did this for any field K, not just for Fp. Okay. Then, as before, we are able to define the ring of integers of an equal characteristic local field as the integral closure of Fpx, which is the ring of integers of the adic completion of Fpx. And then from the general theory about discrete valuations, we obtain that this ring of integers is again a discrete valuation ring. Okay. Now I'll say a few things about what we want to do next. So first, we want to relate global fields and local fields in our formalization, right? So we have seen earlier in the talk that whenever we start with a Dedekind domain and we complete it at some maximal ideal, then we get a discrete valuation ring. But here we want something a bit more specific. So here we want that, two different cases. So first we want that if we start with a number field f and we fix any finite place b of f of characteristic p, then we want to show that the completion of f at the place b is a mixed characteristic local field with residue characteristic p. And then the second result that we want to prove is that if we start with a function field f of characteristic p, and v is any place of b because any place is going to be finite, then fv is an equal characteristic local field with residue characteristic p. So this is in some sense our most immediate goal that we want to prove. But we also have a far-reaching goal that we are working towards, and that goal is local class field theory. So I won't get much into the details of local class field theory here, but I will say that this is a part of number theory in which we are trying to understand the abelian extensions of a local field K, and also the Galois groups associated to these abelian extensions in terms of the arithmetic of the field. So this theorem that I'm showing on the screen is one of the main theorems of local class field theory, and this is one of the goals that we want to formalize in the longer term. So to be able to formalize this, we need several prerequisites, right? So we will need to formalize some results about ramification theory, and we also will need quite a lot results about several commodity theories. So something that we already have are some results from group cohomology, thanks to Amelia Livingston. But then we will need to generalize, based on her work, we will also need to define Galois cohomology, Tate cohomology, and prove many results about these theories. Okay, this is everything that I wanted to say in this talk. If you want to see more details, the code of our formalization is available online, and also the preprint describing this work is available. But I will also be very happy to answer questions now. Thank you very much for listening.
Okay, thank you very much, Maria, for a very nice talk. Do we have any questions? I believe Patrick has a question.
I've got the obvious question, but I was faster. So what about porting all this to Lean 4? Because it
we are working on that. Yeah, we have ported about half of it this week, I would say. So yeah, hopefully soon. Yeah.
And have you noticed anything interesting in what you've already ported? Any difference between Lean 3 and Lean 4 that is especially relevant to your project?
Well, actually, I will probably post this in Zulip next week at some point, but I'm having trouble with intermediate fields. Like for some reason, like some instances that were found in Lean 3 for intermediate fields, like something is an algebra or something is a scalar tower or something like that, they are not found in Lean 4. And I don't know why that is. I've been trying to fix it. I was able to get some of them, but like some of them are still not found. So yeah, I should get a minimum working example and post that on Zulip. Yeah.
Maybe I can add just one thing to Patrick's question. In the port, I think we also run into some problems. We were discussing this with María Inés about coercions. There are a lot of coercions when sometimes you want to see things in Z, sometimes in multiplicative Z with 0. So there are some coercions. Well, it's very easy to fix, but so you have files with 50 errors that are 50 trivialities, but still you have to go through these 50 errors. So they are treated in slightly different ways from Lean 3 and Lean 4, but it was nothing painful.
So there is something with elaboration here going on.
Yes.
So maybe you would need a more specialized elaborator or something.
Okay, Johan also had a question.
Yeah, thanks for the talk. So my question, I also asked it on Zulip, but I can ask it here as well, is about sort of connecting with MathLib. John Oegster wrote a file about mixed characteristic rings and some sort of induction principles for properties of rings, where you can do case splits on mixed characteristic, equal characteristic, etc. So my question is, are you aware of the existence of this file? And if so, are you using it and or integrating it? Because there are some to-dos in that file related to local fields, p-adics, etc., where it's not yet shown that they're mixed characteristic. So I don't think it's exactly like there doesn't seem to be duplication with your definition of mixed characteristic local fields. Because he's really working on local rings. I'm just, yeah, there seem to be connections there, or room for connections.
Yeah, thanks. No, I was not aware of this file, so yeah, we should probably look what is done there and see if there are any connections that we can implement. So yeah, thank you.
Okay, I posted the file name on Zulip.
Okay, perfect.
Okay, is there one last quick question? So if not, well, let's all thank Maria again.